Okay, in a previous example, we reviewed this particular graph where we were talking about a corollary that told us about when a function was increasing or decreasing relative to its derivative. What we're going to do now is discuss what happens when we achieve a minimum or maximum on a function. So what I'm going to do is I'm going to write out what's called the first derivative test for extrema. All right, and I'm going to write this in as simple terms as I can. All right, so what are extrema? These are minimums or maximums. So what we're going to do is we're going to analyze, all right, f prime of x, and if the derivative, all right, goes from, okay, what do we say? Positive to negative. All right, and actually let me use an arrow. It'll be a little bit easier understood. If it goes from positive to negative, and then if it goes from negative to positive, we have two different results. So what we're going to do is we're going to use the graph that we were working with before to determine this. So first thing I note is that I've got these two critical points, -2 and 2, because that is where my tangents are 0. All right, I have horizontal tangents. All right, so it's pretty easy to see from the graph that you have a maximum and a minimum at -2 and 2 respectively. But let's understand what the behavior of the derivative tells us so that we can finish filling out this thing for the first derivative test for extrema. Well, notice for it to be a maximum, the derivative had to go from positive to negative. Okay, again, for it to be a maximum, it had to go from positive to negative. So this one right here is where I will write local max. And then if the derivative goes from negative to positive, so that's this right here, negative to positive. Okay, if it goes from negative to positive, then we have a local minimum. Okay, so I'm going to utilize the wiggle graph that I've already written out here to write out that if it goes from positive to negative, I have a maximum here. And if it goes from negative to positive, I have a minimum here. So as you can see, if you've got the wiggle graph, which basically is a line graph that analyzes the behavior of the function, you really don't need the graph, but you do need to know the function and its derivative and where the critical values are, meaning where is the derivative equal to 0 or where the derivative is undefined. Okay, so let's go ahead and take a look at two examples, and we're going to go all in taking the derivative of those two functions. So let's go ahead, pause for a second, regroup, and take a look. Okay, so on these examples, we're going to identify the extreme values, if any, and state where they occur. So what we're first going to do is we're going to take the derivative. So here's f prime of x, and I'm going to get -3x squared minus 18x minus 24. All right, and then what I'm going to do is I'm going to set it equal to 0. But before I even do that, I'm going to try to simplify by factoring. I'm going to factor out the greatest common factor, which is -3, x squared plus 6x plus 8, and I set that equal to 0. Okay? All right, now that I've done that, I can continue to factor. So let's actually erase the 0. So I still have my -3. I want the factors of 8 that add to give me 6. So that's pretty straightforward. That's 2 and 4, x plus 2 and x plus 4. Now I can set it equal to 0. So I have each of these two factors equal to 0, and I get x equal -2, and here x equal -4. And again, these right here are what we call the critical points. All right, so I'm continued throughout these videos to reference the previous vocabulary that we learned. All right, now what we're going to do is we're going to draw out what I call the wiggle graph. So here is the graph for analyzing the first derivative. All right, so on this wiggle graph, I'm going to put the numbers -4 and -2, and of course we cannot forget the infinities. All right, and what we're going to do is we're going to pick some test points before, in between, and after our critical values or our critical points, and we're going to plug them into the derivative for x. So you'll plug in numbers, all right, and I'm just going to kind of fast forward this. You're going to plug in those numbers right in here. All right, now if you're using a calculator, you can use the table of values to verify this, but you'll pick a number like -5. When you plug in a number like -5 into this derivative over here for x, all right, you're going to get a negative number. So let's put a negative sign there. If you plug in a number like -3 in there, you're going to actually end up with a positive number. And if you plug in a number like 0, which is after -2, you're going to get a negative again. So as we notice from the previous information that we looked at, the derivative goes from negative to positive across -4. So if it goes from negative to positive across -4, we say then that is a minimum. And if the derivative goes from positive to negative across -2, we say that is a maximum. All right, that is a maximum. Okay, so not much more to it than that. Now we just basically write out our answers, and that is to say that we have a local maximum at the value x equal -2 and a local minimum at the value x equal -4. Okay, so pretty neat. Again, the wiggle graph comes in really handy, but this is where we're applying the first derivative test for extrema. Okay, so let's go ahead and take a look at one more example here, and this one is actually really nice and really simple, but again, I already know this stuff, so you'll go ahead and see in a second. We start off again with the derivative. We have 3x squared plus 24x plus 48, and what we're going to do is, again, we're going to set it equal to 0, but before we do that, factor as much as you can. We factor out the greatest common factor, leaving us with x squared plus 8x plus 16, and then we have the factor, we're looking for the factors of 16 that add to give us 8, and that right there is going to be 3 times x plus 4 times x plus 4, because 4 and 4 is 16 and 4 plus 4 is 8. All right, so really when you think about this, looking at both of these two values, we only have one critical point, and that is -4 when we set this equal to 0. All right, so again, I'm going to write out that this is a critical point. All right, and now we draw our wiggle graph. There's our wiggle graph. All right, again, we're just analyzing the behavior of the function. I'm not going to forget my infinities. All right, so now you pick numbers or test points, if you will, before and after -4, and you're going to plug them in here for x. So we're going to be referencing this right here, maybe not so much the 0. All right, we're going to be referencing this right there. All right, and when you plug in numbers, just so happens you could pick a number like 0, which is to the right of -4. You're going to get a positive number. If you plug in a number like -5, you end up with a negative and a negative, which is positive. So it really doesn't change sign. Derivative doesn't change sign at all. -4 is still a critical point because that's where the derivative is 0, but it's not a point at which we have an extrema. Okay, so we don't have a minimum or a maximum. So therefore, we say that there are no local extrema, and that is definitely a possibility with some of these functions. But I'm pretty sure if you look at the graph of the original function f of x, you'll see why. All right, I'm not going to get into what the graph looks like because it's not always necessary to use the graph to analyze these. It's all about the calculus and doing the calculus and figuring this stuff out for yourself. So again, I hope this video was helpful. Remember, like and subscribe.